Hello, my name is Jerome Jacobs, and I am a sophomore biomedical engineering here at the University of Connecticut. At UConn, I am a Rowe Scholar, and I'm very interested in integrating new engineering technologies into the medical field. Over the summer, I did my holster project on developing and validating a wearable armband biosensor for continuous blood pressure monitoring. So this is my presentation outline. I will first begin with my research context, or the reasons why I wanted to pursue this specific research topic, the project timeline and tasks, my research process for obtaining my data, the research outcomes, what my data was, as well as my reflections of the overall experience. So research context, there was a lot of personal reasoning that went behind specifically blood pressure monitoring. My personal family, both my mom and my dad's side, has quite a history of heart disease or heart illnesses in the family. My Korean grandfather on my mother's side actually suffered 3 heart attacks in 2 years, and my uncle on my dad's side also suffered a few heart attacks or some heart disease issues. And so cardiovascular disease being the leading cause of death among US adults, one person dies every 37 seconds, and this is just in the US alone, not to mention worldwide. High blood pressure, hypertension is a major contributor to the causes of these diseases, and it is a silent killer because about 60% of US adults are not aware of any heart disease symptoms until their first event happens, their first heart attack or their first stroke occurs. Several studies emphasize the critical role of continuous blood pressure monitoring, which actually does not currently exist on the market. And so my research was focused on trying to obtain continuous blood pressure monitoring through ECG and PPG signals. As of today, there is no FDA-approved continuous blood pressure monitoring devices available for the public or for medical purposes. Most people assume that their Apple Watch or their Samsung Galaxy Watch is for continuous blood pressure monitoring, because when they exercise, they see that the numbers go up and down, when actually the reason these commercial smartwatches are not good for medical data is because they are not used for cardiovascular disease diagnosis or treatment by doctors. They have no protection against HIPAA, and the different measurements between heart rate, which is what most of these instruments measure, is very different from blood pressure, as heart rate is counting the number of beats per minute that the heart is working, and blood pressure is detecting the force of blood flowing against the arterial walls. The American Heart Association requires an accurate blood pressure measurement for CVD diagnosis and management, which is why Samsung Galaxy Watches, Apple Watches, any other smartwatch technology that says it has a blood pressure monitoring system will not be, the data from those will not be available to use by medical professionals. So my project timeline and tasks. This is after multiple drafts of trying to come up with the best case scenario of how well I could flow through all my research. I've split it up into a section of 10 weeks, weeks 1, 2, 3, 6, 7, 9, and 10. Weeks 1 and 2 focused mainly on reviewing literature I had conducted prior to my holster project starting, as well as becoming familiar with PCBs, printable circuit boards, using a program called Altium Designer, which is very widely used amongst engineers. Weeks 3 and 6 was actually ordering a printable circuit board online and getting sample ECG and PPG sensors from my mentor, Professor Kim, as well as developing codes with Arduino and learning more about SPI communication and how that will factor into my final project. Weeks 7 through 9 primarily focused on data collection, so me doing through trial and error, enhancing my algorithm for detecting continuous blood pressure. And then week 10, validation and experimentation, produce and analyze multiple versions of figures and graphs in Matlab, which is the mathematical program that I used, as prototype evaluation and validation, as well as finalizing my prototype and continuous blood pressure monitoring algorithm. So the research process, as I mentioned before, research processes weeks 1 through 4 focused on 2 major topics, reviewing literature and PCB manufacturing, as well as Arduino. Arduino ended up being a much more important aspect of my project than I had originally perceived, and that is because the Arduino Nano BLE 33 BLE Sense, as pictured here, will actually be the chip that you will have on your armband. So this is where all of the data that is coming from the ECG electrodes on your body will go to, will transmit to. SPI communication, also very key to my project. What makes SPI communication different from other interfaces is the ability for the codes of 2 different microcontrollers to go to each other simultaneously, which is important for continuous blood pressure monitoring. As you can see here, this is not what the SPI communication will actually look like when my final design, but this was just showing how with 2 Arduino microcontrollers, I was able to use a push button sensor to turn on and off an LED using the SPI communication interface. And then here is just a sample of the code from my slave microcontroller that I had presented for you. So research process 5 through 10 focused on data collection and algorithm development. As shown here, this is what the current PCB that I have and what I would like to include in my final project. This PCB is the ADPD4000Z evaluation board. And as shown here, I have 3 ECG electrodes soldered and solidified with electrical tape. And this is what will be on the chest portion of your body that will help, through SPI communication, send signals back and forth to your Arduino armband. And then here, this is the program, Device Studio 5, which I used primarily to calculate my ECG and PPG data. How this works is on the evaluation board itself, there's a PPG sensor. So what that will happen is once the PPG sensor touches your skin, it'll start collecting PPG data, where the electrodes, the ECG electrodes, will simultaneously obtain data at the same time, which will be graphed here in ECG and here in PPG. So continued weeks 5 through 10, my Matlab was a very key part of this process, especially in the later weeks when I was developing my algorithm for continuous blood pressure monitoring. As you can see here, I have multiple trials throughout months of research, and it was very difficult for me to accurately get a good ECG reading. My professor and I were talking, and we were trying to figure out if it was a slip up in instrumentation or if it was a slip up in coding. But after many trials and errors, we finally managed to get probably the most spectacular ECG reading I've ever gotten. And this is very key because, as you can see here, there's very consistent peaks in ECG that I will later use to calculate the R distance, which is the distance between each individual ECG peak, which will help me obtain a calculation for accurate blood pressure. And I really, really enjoy this graph because it really shows how you can get a very good result and how you can get a very maybe skewed result at the same time. Because as you can see here, between 45 and 65 seconds, there's a very accurate, steady PPG and ECG sensors that are working very well. And then after 65, the instrumentation goes a little bit haywire. But right here, this portion of the data really shows that the ECG sensors and PPG sensors are working well. So research outcomes. I managed to successfully use SPI communication between 2 Arduino microcontrollers. SPI communication is what I will then use to send ECG and PPG signals to my PCB device. So that was one success of my research. I managed to integrate both ECG and PPG sensors into my PCB board so I could obtain the signals that I needed. I created and analyzed multiple models as shown before through graphs and tables of the ECG and PPG data, which was challenging. However, in the end, I was able to accurately collect that data and I can continue to pursue my project. Since I have figures with accurate PPG and ECG data graphed together, my next step is to then begin calculating the R distance, as I mentioned before, the distance between the ECG peaks, to therefore calculate continuous blood pressure. So my project, as of now, is still continuing, and I'm very excited to keep working on my device this coming semester and in the coming year with Professor Kim. So my reflections, integrating my passion into a scientific research project as a freshman was a very, very amazing experience, and I want to really thank the Holster board for giving me the opportunity to pursue a research project that I was passionate about. There was a very steep learning curve for Arduino, SPI communication, and Matlab. I do admit that before I started this project, I had very limited experience in all three areas. In fact, I barely knew what SPI communication was before I started this project. But after just a period of 3 months, I am very proficient with both Arduino coding and SPI coding, and I'm getting better with Matlab each and every day that I'm working on improving my algorithm. So that was another very positive takeaway from my project. Experiencing a true sense of trial and error approach in research. Holster is definitely the research project where I had the most trial and error, especially because it occurred over multiple months. There were many times where, especially when I was trying to calculate ECG data, that I got a little frustrated, but I knew that I was working towards a greater goal, and that really helped me kind of persevere and push through, and I'm very happy with the data I ended up collecting as shown in the figures. I also realized the importance of one-on-one faculty mentorship. Professor Kim was amazing with me ever since day one when I came to his lab asking for an opportunity to help him with his research. And my Holster project was a very unique and invaluable experience, and by pursuing a research project under the current circumstances was a challenge, but I enjoyed every step of my Holster project, and my next step is to use the ECG and PPG data to accurately calculate blood pressure. And then finally, acknowledgements. Thank you to Mr. and Mrs. Holster for providing your generous funding for the project, to UConn Honors Program for giving me the opportunity to apply to Holster, to Dr. Moscardelli and the Holster Board Project Development Seminar for helping me, supporting me in developing my project through my proposal and my timeline and my budget. And then lastly, but most important, to Professor Kim, who was my faculty advisor, who helped me every step of the way and was great with communication and really helped me whenever I was stuck. So thank you, that is my presentation.